Test, testing a claim about a proportion. Now that we've learned the basics of hypothesis testing, we are ready to test for specific situations. So all those specific situations we mentioned before that we'd get to later, now we're going to take a look at those. In this section, we will learn how to test a claim about a proportion. We also, in future notes, will look at testing a claim about the mean when the standard deviation is known and when the standard deviation is not known. But for now, we're just going to work on proportion. Before we get started, let's review the basic steps of any hypothesis test. First thing you want to do is state the null and alternative hypothesis. Make sure the equality is with the null, so whether it's exactly equal to, greater than or equal to, or less than or equal to, that will be the null, and the alternative is usually something that's opposite. Step 2, find the critical value from the appropriate table. Z or T depending on the situation. 3, compute the test value. You'll also see the word or hear the word test statistic. That means the same thing. Step 4, compare the test value or test statistic to the critical value and rejection region that you found in step 2. Step 5, make the decision to reject or not reject the null hypothesis, or fail to reject is another way we say that. And finally, number 6, summarize the results in the context of the problem. So don't just say, yes, we rejected or we failed to reject. Talk about what that means in the context of the problem. Okay, so that summarizes pretty much everything we did in the previous section. And if we're testing for proportion, this is our test value. So we have a Z, and knowing that we have a Z, we know we're going to be using the standard normal table. But for a proportion, Z is equal to P hat minus P over the square root of P times Q divided by N. So P hat is X over N, which is the proportion from the sample. And usually we'll be given those numbers X and N, and we can calculate P hat ourselves. P is the proportion from the population. Most times it's given to us as a percentage, but that's what P is. And then N will be the sample size. Now the first problem we're going to attempt, we'll use the traditional method of hypothesis testing. In the second problem, we'll learn a slightly different method. They both yield the same results, but it's just a different method. Example 1. The local school board has been advertising that at least 65% of voters favor a tax increase to pay for a new school. A local politician believes this number is overstated. To test his claim, he asked 50 of his constituents whether they favor the tax increase, and 27 said that they would vote for it. If the politician wishes to be 95% confident in his conclusion, does this information support his claim? Okay, so we're going to go through a traditional hypothesis test. And the first step is to state the null and alternative hypothesis. Well, for the null, what we're saying is that notice we have this word here, or these set of words, at least. So that means 65% is the minimum amount of voters that the school board believes is going to vote in favor for the tax increase. The way we would express that is to say that P is greater than or equal to 0.65, which means the alternative has to be the opposite of that, which is less than 0.65. So that's what the politician probably believes, that since he said that number is overstated, he thinks that there are fewer percentage of voters that will vote for this new tax increase. Okay, step 2, we want to find the critical value. It would also help at this step to identify which type of test you're doing, left-tailed, right-tailed, or two-tailed. And because, remember, we always look at our alternative statement to determine the type of test we are doing, because we want P to be less than 0.65, that means we are doing a left-tailed test. So good idea to identify that here in step 2. So what's happening, and we know we have a normal curve since we have z-scores. And we have some z here that I don't know, but I do know this area. Now we were told to be 95% short. Well, that means alpha is 1 minus 0.95, which is 0.05. So 0.05 represents the area here in this left tail. What we're trying to find is the z-score that cuts off and gives us that 5% in the left tail. So this is an inverse, inverse normal, if you will. So in your table, you want to look for 0.05 and see what z-score that gives you. So it looks like right here, nope, that's too small, that's 0.005. Let's go down a little bit further. So right around here, we have 0.0505 and 0.0495. And each of those is on either side of 0.05 exactly. So it looks like we're looking at 1.6 or negative 1.64 and negative 1.65. And some books will actually label that number for you and say negative 1.645, which is halfway in between those two values. If you chose to use your calculator on this one, you should get something very, very close to that. So our critical value, which is that z-score that gives us a 5% area in the tail, is negative 1.645. And we know it's negative because we're in the left tail. Okay, third step is to find the test value. And this is the one we hadn't done up until now. So our test value for a proportion says that z is equal to p hat minus p over the square root of pq over n. Well, p hat comes from the sample that the politician took. And he talked to 27 or 50 of his constituents, and 27 said they would vote for the new tax increase. So now when we go to set this up, p hat is 27 over 50. Regular p is what was stated in the hypothesis, the 65%, so 0.65, divided by the square root of 0.65 for p. Remember, q is just 1 minus p, so that'd be 0.35, divided by the sample size, which was 50. So we put all that in our calculator. Be sure to use parentheses around the numerator here when you do put that in your calculator. And I'm getting negative 1.6307 when I take that out to 4 decimal places. Okay, so step 4, we want to compare that to the critical value. So I'm just going to copy this here, this little picture we drew previously. And this area out in the tail, remember, that's our rejection region. So if I have a value that falls out here, then I'm going to reject the null hypothesis. Anywhere else, then we're okay. Well, this 1.637 is just to the right of negative 1.645. So it does not fall in the rejection region. So for our conclusion, or a decision rather, we fail to reject the null hypothesis. So for our conclusion, we would say there is evidence to suggest the proportion of voters who favor the tax increase is at least 65%. Now, we didn't prove that. All we're really saying is that we didn't prove it the other way. We didn't prove that it could be less than that. But because we did not reject the null hypothesis, it pretty much stays in place, and we can say that there is evidence to suggest that that's probably right. So again, we're not proving it. We're not saying without a doubt for sure it's 65 or greater, but we're saying that we can't prove it another way. Okay, now in example 1, with finding the critical value and the test value and comparing those, remember that's called the traditional method. Another way to test is to compare the p-value to the significance level alpha. Well, what is the p-value and how do you find it? The p-value, which be really careful not to confuse that with p, the proportion of a population, is the probability value. And it represents the probability of getting a value at least as extreme as the one representing the statistic from the sample data. So it's saying it has to do with the probability that I'm going to get something as far out in the tails as what I'm getting from the sample data. I think this will make more sense once we get into an example, though. So in our whole process for hypothesis testing, the only thing that changes is in step 4, instead of finding and comparing the test value to the critical value, we're going to find a p-value and compare it to alpha. So let's try that in the next problem. Example 2. An educator estimates that the dropout rate for seniors at high schools in his state is 15%. Last year, 38 seniors from a random sample of 200 seniors in the state withdrew. At 0.05 level of significance, is there enough evidence to reject the educator's claim? Well, we're going to start off exactly the same way we did before by finding the hypothesis. So we have the null hypothesis and the alternative. Remember, the null usually has some form of equality in it, and it's usually the number that's been in place historically. Well, an educator thinks that the dropout rate is 15%, so that's going to be our null. And in our question, we're saying, is there enough evidence to reject the educator's claim, meaning we just don't think that it's 15%. Now, there's no indication of that it's more than 15% or that it's less than 15%. So this is when we would say P is not equal to 0.15. Okay, generally the second step is finding the critical value. And remember, you also want to decide which type of test you're doing here. Well, since our alternative hypothesis says not equal to, so we're not saying greater than or less than, just not equal to, this is going to be a two-tailed test. So the alpha, the level of significance they gave us, 0.05. And we actually looked at that up previously, but it's going to be a little bit different here. Because what's happening is instead of that 0.05 being concentrated in one tail, we have to split it up among two tails. So that means the area in each tail is simply 0.025 if we take that 0.05 and divide it in two. So now, instead of looking for a z-score for 0.05, I'm looking for a z-score for 0.025. And it doesn't matter which side I find, because remember the standard normal curve is symmetric. So I only have to find one, and I automatically know the other. So looking on our table here, 0.025. Up right here, right on the nose. And it looks like that's happening at negative 1.9. So right here. And 1.96. So that means the z-score is 1.96 down here and negative 1.96 down here. Okay, third step, we're going to go ahead and find our test value. And it's exactly the same way as we did before. So z is equal to p hat minus p over the square root of p cubed divided by n. P hat comes from the sample of seniors that they spoke to. They sampled 200 and 38 of them withdrew from school. So that's our P hat. So then when I go to set up my formula here, that's 38 over 200. There's my P hat. P is the value that was stated in our hypothesis, so that's 0.15, divided by 0.15 times 0.85, 1 minus P, all over 200. Let's see what that gives us. And let's see, for me, I'm getting 1.58. And just a little note to know if these values are coming out right from your calculator, because it's very easy with the syntax to forget a parentheses, especially with the graphing calculators, and to make sure you're getting a value that's reasonable. Your test value should be somewhere in the range of 0 to 3.5 or so. Because remember, the whole thing with standard deviations on our standard normal curve is that the majority of our data is contained within 3 standard deviations of the mean. And this z-score is a standard deviation. So if we're getting something very, very large, such as 5 or 10 or 15, then that doesn't make sense in the context of standard deviation. So if you're getting something kind of strange, you might want to double check that your parentheses are entered correctly, that you didn't forget a decimal or anything like that. But usually something between 0 and 3.5 is what you're going to end up with. So we got 1.58 here. Okay, so here's where the change happens for p-value. For p-value, I'm going to look up the area for the z-score 1.58 from the previous step. So what's happening here is I have my test value or test statistic, and I know it's 1.58 here. What I'm looking for is this area. I want to know what that is. So I go to my normal table, and because this is a tail value, I'm going to use the negative values, but we know that we're really on the positive side. So 1.58, there's 1.5, and go all the way over. So we're right here, 0.0571. So this area .0571. Now here, and I'm going to show you both methods side by side. Even though we're doing the p-value method, I want to show you how we'll get the same results. What we're supposed to do here in step 5 is compare the p-value to alpha. And if it's smaller than alpha, then we reject the null hypothesis. So if the p-value is less than alpha, we're going to reject H naught. So the p-value we got was 0.0571. And I'm comparing that to alpha, which for us was 0.05. Well, 0.0571 is larger, so we would fail to reject the null hypothesis. Now compare that to, and this is just for comparison, the traditional method. The traditional method would have us look at the critical value, which notice we didn't really need with the p-value, but I just kind of threw it in there anyway. So we found the critical value to be 1.96 and negative 1.96. And if we put our test value or test statistic in there, we got 1.58, which falls right here. Well, we get the same conclusion because 1.58 is not in the rejection region. So since 1.58 is not in the rejection region, we fail to reject H0. So same conclusion, just different method. So the traditional method, you're comparing the test value to the critical values, but with the p-value method, you're comparing the p-value that you find from the test statistic or test value to 0.05. If it's smaller, then you're going to reject because that area is smaller than what we should be getting. But if it's bigger, then you fail to reject. Regardless of the method, we still need a conclusion. And we would say here in the context of the problem, there is evidence to suggest that the dropout rate for high school students is not different from 15%. So again, we didn't prove that it's 15%, but we don't have any way to say that it's either smaller or lower than because we didn't get a test value or anything that fell in that rejection region. So make sure you work on both methods. Traditional method, you're comparing the test value or test statistic to the critical value, whereas the p-value method, you're comparing the p-value, which comes from looking up the area on the test value, to alpha. So really in the p-value method, you don't need that critical value that we found in test 2, but for the sake of comparison, I found it here.